All right. Hi, everyone. Thanks for joining the August 2022 session of the Fission Reactor. We have some, I think, exciting developments this time around with some differential data log stuff. And then also, though, some of the stuff behind the scenes, which maybe we can get into near the, at the back end of this is, Corinne and I were talking recently, but actually, I think we're almost at the point where we can start actually writing this stuff down soon. And so if you follow the Fission spec repo, there's a little bit of text, literally the first couple of sentences in a PR, and that's going to get expanded over the next couple of weeks here. So without further ado, Quinn, how's differential data log treating you these days?
I've been having so much fun. So a lot of what I want to talk about today is kind of an extension of what I brought up last time. So for those of you who were here, you might remember that a big focus was on differential data flow and my theories about how it might be a really good fit for the sorts of things that we want to do with dialogue. And for those of you who weren't here, I'm just going to talk a little bit about differential data flow for a moment. It's a high-performance stream processing library in Rust by Frank Macheri. He uses it at his company, Materialize. But really the big thing with differential data flow is that it allows you to represent computation as these circuits of stream operators. But what's special about these circuits is that they can operate over incremental and differential data. So that rather than needing to perform an entire computation in batch every time, you can just operate over deltas and really efficiently compute your results from that. And so that idea was what kind of got me looking at differential data flow about a month ago. It's actually also a project that VMware is using as a compilation target for one of their projects, differential data log. And I think they were seeing a lot of the same potential there as a way of incrementalizing data log by compiling it to these circuits that can operate over deltas rather than doing a more traditional data log evaluation where you recompute from scratch every time. So I spent a little bit of time playing with differential data flow, and I actually implemented RGA in it. I took what would be the traditional data log implementation of RGA, and I implemented that in differential data flow. And that's a program that is kind of notorious for not being very incrementalizable using more traditional algorithms like DREAD. There's plenty of benchmarks that have it coming in at taking well over a minute to run through a data set of about 260,000 events. But with my implementation in differential data flow, I actually processed all of those in about 400 milliseconds. So that got me very excited about differential data flow. And I wanted to understand it more. And I actually spent the past couple of weeks implementing a part of it in Elixir to get a feel for how the system works and whether it's something we might be able to use in dialogue. So I'm going to share my screen a little bit. Can everybody see this? Cool. So I just have a little notebook here that shows off my port of differential data flow in Elixir, along with some of the things that I'm doing with it. One thing I do want to stress is that this is a pedagogical implementation of the system. Really, I built it so that I can understand what's going on and how it fits in with what we're doing. It's not focused on performance, and anything you're seeing here in terms of syntax and API is not what we are going to be pushing for the user-facing interface for dialogue or anything like that. Really, what I'm focusing on in here is the underlying ideas and how they might help with our implementation. So first off, I just want to show off a really simple circuit. This is a circuit that computes the 2-hop paths within a graph. So as input, it basically takes in 2 sets. One is a list of vertexes in a graph that you should avoid, and one is a list of edges between vertexes in a graph. So then I just defined this little circuit here. I have a little API for building circuits, and we basically just wire up these 2 sets. We index them, and then we join across them to try to find the paths that cross through 2 edges, but do not go through one of those avoid nodes. So we join them, we do an anti-join, and then we output the result. That gives us all of those paths, but more interesting is the circuit that we actually generated. And this is what this program compiles to. we basically have all these different differential operators that operate over values within the stream. And then as deltas come in, you're able to really efficiently compute over those and integrate them into the results from previous time steps. But this program itself isn't super interesting. And another thing that you get with this data flow model is the ability to encode loops and recursion, which is really essential for data log. So this is another really simple program that just implements Fibonacci. This time we just have a generator that keeps outputting, it outputs either 1 or 2, or sorry, 0, 1, or 0, depending on the time step. And then we just have these feedback loops that introduce cycles into the data flow graph that allow you to do that iteration that's required to compute Fibonacci. So running it 11 times, we get the first 11 Fibonacci numbers. And we also have this graph with the loops that encode those recursive parts of the algorithm. But really what I want to be talking about is how differential data flow helps with incremental view maintenance. And all of these programs so far have been fairly static. This next one, though, computes transitive closure. And this time I'm doing something a little bit differently in the data set. Instead of having one set that I return, I actually have multiple sets, and I'm going to, at each time step, return the next one in sequence. So in the first time step, we're going to add an edge from 1 to 2, in the second, from 2 to 3, and so on. You might also notice that sometimes we are removing edges, and that's something that the circuit can handle. So this time, very much the same program, or very much the same idea, but this time we have a recursive subcircuit that's actually being used for the transitive closure piece. So essentially, when we have a graph, we can compute the paths in the graph by considering edges between nodes to be a path, or by considering the joining of a path with an edge to be another path. And again, when we run this, we get the output for every time step. But what's really interesting here is that at each step, we're introducing deltas into the system. And what we're getting out is the total materialized view for that time step. And that might seem a little bit weird, but the way that works becomes a little bit clearer when you look at the circuit that gets generated. Because what this system is actually doing under the hood is defining a calculus over streams that allows you to differentiate and integrate over these streams. So in this case, when we have this recursive subcircuit to compute the paths, what we do is we import this edges relation with this delta 0 operator. And this essentially emits a stream that will have the values of the parent stream for the first time step, but then 0. And so that kind of jumpstarts our computation and does like the base case for the recursion. But then when we're doing the joins in here, they're actually going through these feedback loops, these weird trace append dissections. And this is actually how you persist data forward in time through the circuit. You just introduce these feedback loops that take the data from the previous time step and then pass it into these delay nodes. That's these Z1 nodes here, which just return whatever the value was at the last iteration of the circuit. So essentially, these allow you to keep replaying the previous result and kind of using that as a way of maintaining state within the circuit between iterations. But then where all of this comes together is that once this inner circuit reaches a fixed point, once it's done computing and there's no more paths to find, it actually integrates the stream. So when it exits, it does this integrate trace operation. And that walks across all of the timestamps that are associated with the circuit and basically adds together the number of derivations for every tuple. Every tuple has a weight associated with it. That's the number of ways it can be derived. And this integration step just allows you to add up all of the results from all of the iterations of the loop, while also canceling out anything that may have been deleted as a result of that calculation. So the end result is that we end up being able to materialize the view at any timestamp by just treating these streams as like an algebra that we can perform calculus over. But these programs I'm showing you are super low level, and they're not really something that we'd expect anyone to write manually. So I also wrote a compiler from Datalog to these circuits. And here I have a small example of transitive closure here. This data log supports aggregation, joins, negation, that sort of thing. It's all stratified negation. But what's very cool is that because this is compiling down to differential data flow, it's actually generating these incremental circuits from the program. So when I have this output relation that that's meant to represent the number of paths from a node, that's actually going to be computed incrementally. We're not going to, in every iteration of the data log evaluation, count all of the paths up. It's incremented using like linear operators that we're able to combine together using those calculus rules to just efficiently use the new deltas to compute the new result based on what we have stored. So this is just a rough DSL I threw together, but I have a compute paths rule, which is going to write to the path relation. It has 3 pre-variables, and it has 2 clauses. In the base case, we're just going to produce a path whose source is X and whose destination is Y. If there's an edge whose source is X and whose destination is Y, that's the base case. But then the recursive case instead is going to create a path from X to Z by joining on paths and edges. So if there's a path from X to Y and an edge from Y to Z, then there's a path from X to Z. And similarly, to count the paths, this just shows off aggregation. So there is going to be C counts for paths starting at X. If there is, but if you basically take all of the paths whose source is X and then count them and bind the result to the C variable. So just hooking all of this up then, we can pass in our edge set. We can hook up some sources and sinks. These are how you get data into the system and out of the system. In this case, I have a couple defined. As the source, we're just feeding in this constant set of edges. And as the sinks, I've got 3 of them. And all of them are this 2 ETS sink I defined. So within Erlang, there's a system called ETS, Erlang Term Storage. It's basically a tuple store that you can use within the VM, sort of like having like Redis or something inside the VM. So literally what I'm doing here is hooking up sinks at the end of the system where such that whenever a new tuple is written to either edge, path, or path count, those tuples are going to be propagated to these ETS tables. And then I also just have a couple helper functions set up for the demonstration here. So if we run this, it's going to output at every time step the edges from that ETS sink, the paths from that ETS sink, and also the counts for the paths. So we can sort this, see that there's paths from 1 to 3, 1 to 2, and so on. The weights are the number of derivations of these paths. Or sorry, these are edges. This one down here is paths. But then, yeah, we also have the path counts. But again, this example is using static data. Oh, yeah, Marc-Antoine, you have a question?
Yeah, quickly. If there's a cycle, will it find many paths at each point of the cycle, like a path version of the cycle at each point, at each node?
Yes and no. So at the output of the system, and honestly, I probably should have removed this weight column. I have it here because it was helpful for me in developing the system. But internally within the system, you have bag semantics, and tuples can have multiple derivations. But then when you exit the system, you collapse everything back down to set semantics. So in the output here, you're only seeing weight 1. But internally within the system, it's going to detect that there's multiple ways to generate a path, for example. And this is something that you're going to see the relevance of in the next example, because, or you might, I don't remember which example I have next.
And another quick question, obviously you can delete edges, and that works because edges and paths are separate, right? So if, yes, but does the path remember the provenance of I came when this path was introduced, or it's just?
So that's what's really fun about this. And this is kind of where it excels for some classes of problems where something like dread doesn't. Just to refresh people's memory, dread, delete, rederive, is an incremental view maintenance for data log. the works by having a delete step and a rederive step. So when tuples get deleted, you delete those tuples from the start, you delete any tuple that can be derived from those tuples, and then you try to rederive anything that may have had multiple derivations. And the issue here is that you over delete things at the start, and sometimes that over deletion is far too large and really slows things down as you need to kind of recompute everything that you've deleted. But what happens with this data flow approach is that when you delete a tuple, you give it weight -1, and then it flows through the system and causes new derivations to happen. So when you join two tuples together, the weight of the resulting join is going to be the product of their weights. So if you have two derivations of one tuple and -1 derivations of the other, then their join is going to have -2 weight, which will be able to cancel out two positive derivations of that tuple. So you basically just run through the circuit with negative weight, and then that gives you the deltas that you can apply to that like integrated trace that I briefly touched upon. So yeah, this is the circuit that the data log program compiles to. It's very much the same thing I showed before, except with a couple more details for things like traces and projection and stuff like that. But then in this next example, it's exactly the same thing, except this time we're introducing the tuples across different time steps, and we have their weights here. So I probably shouldn't do this live because I was just changing things in my visualization. But if we change this to a -1, that actually, let's not change that one. Let's change negative or 1 to 3 to get a -1. This might not work because I was just tweaking some things and this might be outputting the wrong thing. But this time when we run it, I'm outputting a different table for each time step. So at time step 0, we have the edge from 1 to 2, which caused us to derive the path from 1 to 2. At the next step, we added 2 to 3, and that allowed us to derive the path 1 to 3 and 2 to 3. But then at this next time step, we removed 1 to 3. And okay, yeah, so this is just an issue with the visualization. But at time step 2, there's no new paths that were derived. And
it's correct, actually. There was no edge there, so giving it a weight -1 doesn't cancel anything.
It would, oh yeah, sorry, you're totally right. Because there was 2 ways of getting from 1 to 3.
But there was no direct edge, so your -1 should just have deleted
Yes.
the direct edge if it had been there.
Yeah, you're totally right. So yeah, if we had only had one derivation, this would have showed us as losing that path from 1 to 3. But because there exists another path there, we don't lose any of that information. But yeah, so this is just showing the deltas at every time step. You can get the full materialization by doing that integration process I talked about. You just take like all of the time steps, all of the timestamps that are less than the one you care about and add together their weights. And then that collapses into the materialized view. That's something you can cache as needed and so on. Yeah, I don't want to spend too much time on this example. This one's basically just taken from differential data flow itself, but it's just basically another graph traversal simulating like a corporate hierarchy as you add and delete managers and showing that how that changes the graph. Yeah, I'm not going to talk about that one. Yeah, so CRDTs. I don't have too much to show for CRDTs yet, but I did implement RGA in this. I don't have a great visualization for RGA yet, and I haven't ported it to the data log at DSL yet. I just have the circuit itself. But this is essentially a circuit that computes RGA. It's just a manual translation I did from the data log program to RGA. And the Rust version of differential data flow, it runs through, again, the whole data set in 400 milliseconds. And if you do incremental evaluation in batches of 10,000 events, each one takes between like 20 and 80 milliseconds. So that is well within the range that we would need in order to support real-time collaboration with this thing. I'm not getting that sort of performance with my implementation here in Elixir. but I've not been performance focused here. And if this is an approach that we take for dialogue in Rust, that's definitely something that I'd be very excited to explore. So yeah, there's not a ton to show for this example, but I just processed the first 10,000 events, I think it is, in about a second. And yeah, this is just debugging info for me, showing me the number of derivations of every relation, or the number of elements of each relation, so that I can compare against other data sets. But this is actually the circuit that this corresponds to, which I only show to show how important it is for us to give a higher level DSL like data log, because getting this program working by hand was kind of a nightmare. But the data log rules that it corresponds to are very straightforward and intuitive. So now that I've kind of proven to myself that we can do this and I understand how to translate between the two, I think that this is something that we will be able to think more about going forward. Kind of at the start of thinking about dialogue, I had looked into differential data log, and it had seemed very complex and like something that we may not want to reach for. It seemed super heavyweight compared to just a simple, like, semi-naive implementation of data log. But having gone through all of these hoops now once, I think this system is actually a lot more intuitive than it first seems, and that there's a lot of exciting stuff about this approach. Yeah, so in terms of code examples, that's more or less everything I wanted to show off. My plan is to spend the rest of the week just kind of playing with this system, adding a few more features, putting together more examples, just seeing what sorts of rough edges come out and how difficult it is to implement different pieces of it. Something that has been very exciting about this is how easy it has been to implement data log and extend data log once I had the differential data flow stuff implemented. All of the data log stuff that I showed off was just done like Tuesday night and yesterday. And like aggregation took like half an hour to implement, because like the underlying circuit is just such a nice abstraction for all of these ideas. So so many of the things we care about just fit really nicely into the model. And I'm really excited by these experiments. After that, my focus is really going to be shifting toward ironing out the last couple things we need to figure out for dialogue. Things like serialization and exactly how we want the data to be laid out in IPFS, and how we want to transport it between like IPFS and the front end and so on. And Brooke has also been thinking a little bit about encryption. So I don't know if anyone has any questions about anything I've been talking about here. I've kind of been rambling for like half an hour, but I've been having a fun time with this.
And before we hop into questions, just to expand that list of sort of like what's left. So serialization, so an efficient wire format, which is almost certainly going to be different from how we represent things locally on a single system, right? It's just having really fast in-memory data structures is not going to be IPLD. It just doesn't make sense. Encryption, and so that's both for these graph cases that a lot of CRDTs depend on, but then also looking at things as tabular data. A high-level DSL. Right now, even like both the handwritten circuits, but then also the data log that you're seeing in there, or the sort of mid-level representation that Quinn's written, is more of a almost like an ISA, right? It's like it's this inner structure that we don't want to have to train devs. So we're going to come up with some nice high-level clean API for that as well. There's one more that I'm forgetting. Let me just grab my list really quickly here. And oh, there's one more. I'll throw it in the
Is it
chat.
like the blind bus stuff, or?
No, that's stuff that comes
Okay.
that we're going to build on top of it. Yeah, there's one more, but anyway, essentially serialization and encryption and language are the three really big pieces that remain. There's also some questions about what the exact, from almost like a project management level, what the right order to do things in is. So semi-naive evaluation is very easy to implement. It's like, it's super tiny, but doesn't perform as well. But do we start with that and then add features, or do we do some subset of data flow, ship that, and then start adding in incremental features, things like that. So we still have to figure out the exact plan of attack for the real, the non-proof of concept implementation in Rust and WebAssembly. Anyhow, Philip.
Yeah, so my question is basically, when you have those visualizations of the circuits, on those, like from each node to node, there are arrows. What flows on those arrows, or like how big are the data types that flow across these arrows?
So at every iteration of the circuit, every stream is only going to carry a single value, but what a value means is a little vague. In the formalization, a value just needs to be anything that forms an abelian group. This is actually kind of the crux of the approach, which I think is super cool. I guess not super relevant to your question, so I'm not going to get into that now. But examples of things that fit the requirement would be like single integers, or this data structure that you may have seen. I don't say it here.
These sets with weights, those
Z
stacks,
sets.
essentially.
Yeah. So these Z sets are basically weighted sets where they have, the Z sets are basically like weighted sets where every element of the set has like a value, has a timestamp that it was derived at, and it has a weight. So there could be any number of those within the Z set flowing along these edges. But because you are compiling these computations down to incremental circuits, in practice, for the most part, you're only going to be carrying the deltas along those edges. And that gives you a lot of control over how much data you'll be carrying over them. Like, I can imagine that in a real implementation of Dialog, we might have source nodes that represent a connection to IPFS, for example, where we might configure like a batch size. Like maybe every minute or something, it pulls down up to 1,000 or 10,000 tuples, and then flows that through the next iteration of the circuit. Where that is not the case is when you're dealing with these traces. Traces represent a collection of multiple batches of inputs across multiple times. So like in the circuit, the traces are how you are preserving the previous deltas forward in time so that you're able to join against them and use like incoming deltas to see how they impact the full set. And those can get very large. My handling of traces is really the main bottleneck in my implementation here, because I have a fairly naive implementation of sorted tries. And then traces are just a list of a bunch of different sorted tries. And then I walk across all of them concurrently to find matching keys and so on. In the Rust implementation of this stuff, they have what they call a fuel-backed spine, which is basically a linked list of slots that have like capacities of like increasing powers of 2. And then you keep merging them together, and as they reach their capacity and then starting like a new batch. And that allows them to like really quickly search through these data structures with exponential search. But I'm not doing any of that in my implementation. Does that answer your question? I guess, where were you going with the question?
I mean, yeah, I was going like performance with this question, and I was
okay,
and trying to understand what exactly flows through the circuit. So
yeah,
very much exactly my question. And like these things, for example, you were mentioning trace, it was exactly what I was thinking, or not thinking, but wanting to hear.
With things like trace, you don't even necessarily need to actually like move them across the edges. The edges are more of like a logical relationship. Like in my implementation, everything's immutable, and I'm not actually passing things between different nodes or anything like that. Every node just like the struct representing a node in the runtime has a field representing its output that whenever the node is evaluated, it shoves its output into that field. And then the downstream consumers are just able to read that field. And the other important aspect of this is that even when you're dealing with the really big data structures like the traces, for the most part, all of the operators are written as linear operations over these abelian groups that allow you to generally do work that is proportional to the size of your deltas. That's where a lot of this performance comes from. So when I do like this join, for example, this whole section here with like the two join traces, the indexes, and the plus, that is a join between two different relations that compiles down to two different joins under the hood. This left one is going to be a join between the deltas of the manages on the left side of the relation and the total set on the right. And that, or other way around, it's going to be the deltas for the right manages with the total trace. And then this one is the deltas of the left manages with the total trace. So you're not walking across the entire trace in both cases. You're walking across the small delta set and finding the corresponding keys within the trace. So you like join deltas together and then you join the deltas with the traces, but you never join traces with traces. And for the most part, wherever possible, operators follow similar implementations where you're just really focusing on the deltas as much as possible. There's cases that are not linear where you do need to keep track of everything. And probably the clearest example of that, I don't know if I can, yeah. So when you have a recursive subcircuit, internally, this is going to do a ton of different iterations of the computation. Each of those are going to have their own timestamps associated with them. For those of you who were here last time, I talked about how differential data flow represents timestamps using a lattice. That means that you can have like increasingly refined timestamps that compare together, but do not compare against coarser versions. And that shows up in these recursive circuits where within the circuit, rather than the timestamps being like 0, 1, 2, 3, they're actually going to be a pair of epoch and iteration. So during the first iteration of the circuit, you might have like 0, 0, and then 0, 1, 0, 2, and so on. And what this means is that when you exit the circuit and export the results to the parent, you need to consolidate all of that under the timestamp that the parent is operating under. And to do that while guaranteeing that you can achieve a fixed point, you need to have this distinct trace operation at the output of the circuit that basically just finds all of the unique values and removes their timestamp so that they are basically ready for export. And the only way you can do that is by walking across everything in the trace to make sure that you're checking everything.
This is
talk. Oh, sorry, go ahead.
this is a similarly performance-minded question, but I'm not sure if it necessarily makes sense in the context where all of the stuff is going to end up being used. But is it possible, or does it make sense to like compile these circuits themselves down into like WASM blobs or whatever? And conversely, how hard is it? How much computational effort, whatever, does it take? How expensive is it to like compute the circuits in the first place from Datalog or whatever query language you'll end up putting together?
It has not been my experience that the compilation to the circuits or the incrementalization of the circuits has been a performance concern whatsoever, even in my implementation. I have only written like maybe 2 or 3 dozen circuits, so that's not a massive corpus, but there's not a ton of work that goes into computing the circuits. For the most part, it's just building up a graph data structure, tossing the nodes in the edges, and then replacing non-incremental operators with incremental versions, which for the most part is something that you can pre-compute. Like the incremental version of a recursive circuit is always going to be like a delta zero import, and then the derivative of the internal circuit, and then the like integration and consolidation of the output. So you don't need to do a lot of that live. And it's mostly a case of like following the algebra to figure out what those transformations are. So I'm not concerned about compilation performance.
Maybe just to add on to that as well. So I'm sure that there's lots of very clever compiler techniques that we could use to get these things to go really, really, really fast. The trade-off for our use case is that we're initially targeting the browser and on relatively small stores. Let's call it 1 million facts and below. So when you look at how a lot of other projects work with these things, they do have some heavier process where they'll compile straight down to native code, and then run that over, for analytical processing like overnight, right? I guess they're just massive, massive stores. And one of the relatively unique things that we're doing is working with Datalog at a single user scale, which means all the time that we put into doing really heavy compiler passes is standing in between the user and the result. And so we need to find out, what are we would have to have some good reason to say, okay, when we run this optimization, we gain this huge performance benefit in the typical case for a user. So at least to get started, and until we find that there's a bottleneck, we're going to go with the circuits like sort of as they are. And then if we find that there's, we're doing a lot of, we'll just pick on RGA again, and there'd be this optimization, if we can detect it and special case it or something, then that's something that we can explore. Compiling these into their own sort of like special WASM blobs, we're probably not going to see the performance benefit out of for these use cases. But that's not to say that for a larger use case, that somebody couldn't take this and adapt it to do that ahead of time compilation pass.
Where I see more possibility for optimization is doing more traditional compiler optimizations, like different types of like loop fusion and stuff. Here to do a join, I'm first like filtering the record based on any like bound constants within the bindings for the rule, and then projecting that to only the fields that we care about, and then indexing that. And like in my implementation, that's going to walk across the batches 3 times. So there might be possibility for fusing things together and stuff like that. But I don't expect that sort of thing to be the bottleneck, even for larger use cases than what we're dealing with.
And one of the nice things Quinn and I were talking about this yesterday about query languages and whatnot. One of the nice things about using data log semantics means that that essentially is our, using the terms loosely here, but that's almost our intermediate representation. And so whatever we do as a front end for that, and whatever we do as a back end for that, the actual user programmable semantics stay the same. The data layout stays the same. We don't actually have to change anything for the data that sits on disk. So if we find that we need more of these optimizations, we can add those in, at least we think relatively painlessly, and then also have like, just because I saw somebody put in the chat a moment ago, we can have a down the road a SQL interface and a EDN interface and a JavaScript sort of custom thing, maybe even GraphQL. Right?
Yeah, and the SQL point is a really great one to bring up. The paper that this stuff is based on is actually predominantly about compiling SQL to incremental circuits. Really, the only difference between SQL and Datalog in this context is the introduction of these recursive circuits. So all of the underlying primitives are basically relational operators, projection, selection, joins, and so on. And like what I did up here with a Datalog DSL, it would honestly be pretty trivial, like hours of work to get like a SQL parser in here that lets you do this using SQL too.
I'm just checking I'm understanding the story correctly, and because weirdly, you are proposing to have the rules defined by the user in the data, compiled in the front end to a graph of operations, and the graph operation executed locally. So the notion of making that into optimized could in theory be done offline, right? Like send that to a compiler that would return a WASM blob. But yeah, I understand why it's not vital, because a lot of the logic is running the graph, right?
Yes.
Yeah, well, and also we want people to be able to remember front-end developer use case, right? So people want to be able to pop open the console and play with it. So as a baseline, they need to be able to do these things dynamically. If somebody is going to write rules in advance and compile that down and get that into like at compile time as part of their tool chain, then yeah, there's smarter optimizations that they can run there. But as the first base level, we're going to make it so that it runs dynamically. And then the question is, well, how much of the speed boost can we really get on this size of data? And the answer may be not a ton, right? Like some milliseconds. But for some cases, it might be quite a lot, because you can, for example, with Fusion, right? You can just skip entire steps. But again, if you're doing it on 100 facts, you probably won't see the benefit, right? So.
And sorry, Philip, quickly, I'm interested in another case where your personal fact store is a small part of a bigger fact store, and then you want to distribute the computation or something like that. Is that in the something you're looking at, and how would you do that?
What do you mean distribute the computation? Like the output, or?
No, I have a small fact store, but I want to know something. Like, for example, I want to do a distributed query on everybody's fact store, giving some way to share the costs or whatever.
I see. So that's a really interesting question. And as I'm using it here, I'm not taking advantage of any of this. I haven't implemented this, but
of course not.
Differential data flow is actually designed for clustered stream processing. And in most deployments of it today, you actually spin up copies of the exact same circuit on every node. And then you have a sharding operation that basically partitions your data based on some key, sends it off to all of the nodes. They run through the circuit, and then they pass the results back. almost doing like a sort of MapReduce style thing with these circuits. And that's not something I've explored a ton. It is something that VMware does in their differential data log stuff. Using their system, I have had a hard time developing an intuition for where and how that sort of parallelism is beneficial. There's a couple circuits that I've seen really big performance benefits for running across multiple cores. But like my RGA implementation, for example, no matter what I have done to it, I have not gotten it to perform better under parallelization than I have single threaded. And I don't know if it's because of the structure of the tree or if I just haven't found the right way of partitioning the keys or what, but it seems to strictly make performance worse in every case that I've tried there.
Very interesting. Yeah, I'll have something else about this, but I think Philip, you should go.
Just really quickly back to that. Sorry, Philip. I think it also depends on the exact use case, the kind of data, the volume of data, how long the thing's going to run for, right? So again, it's the sort of things that VMware is focused on are not the things that this project is looking at. And so there may be some differences in how to tune those optimizations. So anyway.
I think if you can like really uniformly partition your data such that you don't need coordination to join across it, then it is probably a good fit. But that with something like RGA, for example, where most of the rules are looking at a node and they care about the parent of that node and also all of its siblings, that, at least intuitively to me, feels like there's not a great way of partitioning that data such that every node is going to have all of the data it needs without requiring that it has basically all of the data or like huge pieces of the graph. It's not like embarrassingly parallel, I guess, compared to like if you have a bunch of entities representing people and you want to compute their age, you could partition them based on their user ID, send that off to each node, and it can run like the birthday calculation.
Yeah, what I wanted to say was simply just picking up what Sodium was saying earlier or asking earlier, I think, and trying to connect that. So like compiling these circuits to WASM, I was thinking like if the inputs to every kind of gate in the circuit is not constant size, so it's sometimes, for example, these Z sets, then I guess that would make it a little harder to compile to WASM. And so likely, yeah, like a one-to-one kind of mapping from component to WASM component or something like that. That's probably not what's going to work that well, but more like as a whole thing.
Yeah, and maybe to expand a little bit on how we're currently thinking about where the queries live, right? Just as a intuition pump, you have a React application and it has an on change, and that on change is going to run some query, not for the entire data set, but for just what this one component needs to see. So it's very different from making a remote SQL call, getting back a bunch of data, digesting it, pulling it apart, and sending that through, right? It's literally, it's like this thing needs this data, and that's it. And could you wrap that in a thing that then converts that into WebAssembly at compile time? Totally, right? But you're going to have lots of really little WASM blobs that now have to get loaded in and spun up, and all of these things where doing that directly in as with a JS interface that gets fed into an existing WASM that's already running might actually be faster. So we're going to have to play with that, but I doubt it's going to be the bottleneck for a lot of things.
Yeah, that's what I think too, based on even my slow implementation of this stuff. The RGA circuit is a very complicated circuit, and it compiles instantly. Like even using my browser notebook here, where I hit submit and it sends the script to like another server running on my machine, compiles there and sends the results back. It's instantaneous.
That that super makes sense. And I just want to clarify, I was mostly just kind of like curious and not like proposing this as a thing that y'all should do immediately. Just
no, it's a good question.
Yeah, no, it's a great question.
It seemed like a neat idea, but also I super understand why it's not like way up high on the priority list, because it screams of premature optimization.
What I do think would be interesting to explore, Brooklyn and I have chatted about this a little bit, but it's way too early to talk about it in any detail. But there could be an interesting use case in using stuff like this as a remote query language too. Like in the same way that with GraphQL, you can send a giant GraphQL payload to a server and then query a graph that way. If there's a compact way of serializing these circuits such that a server can then evaluate them against their data set, then that to me sounds like GraphQL on steroids, kind of.
I think that matters a lot, because a lot of big data sets especially have privacy constraints. So if you could send a query and somehow guarantee that, you know, there will be enough aggregation that anonymity will be preserved, and that's a totally different. I know there's all the snack thing happening, but this is another angle, like distributing queries. And then what I'm hearing, you speak about serialization, but if you have a compilation of data log, that you can send that, right?
Mm-hmm.
And that makes a lightweight query language to carry.
Not necessarily a stable one. Sorry, I cut you off, Brooke.
No, please finish your thought.
So yes, that's absolutely possible. And that's like exactly what like GraphQL does, for example. You can just straight up send the JSON encoding of a GraphQL query. Where that may not be the best path for us is in that we are really excited about the possibility of using this stuff as a compilation target for a variety of different front ends, and sending like the high level data log kind of locks us into that format versus also supporting sending SQL or sending whatever custom query languages people might build on top of something like this.
Well, then you just have to ship a reference to the compiler with it.
Have a Quine with it.
Sorry, I don't want to harp on this too much, but I saw another point about that. Oh, I think I lost it. There was the privacy angle, but there's another angle about sending queries. Oh yeah, of course, the streaming aspect. Instead of sending a query, you're sending a subscription and you're keeping a channel open.
Mm-hmm.
Yeah, so you may be able to, rephrase, there are definitely use cases where we want to synchronize all events coming from somebody else. So RGA is a really good example, right? You're doing a collaborative text, something, yep. You just want to keep that socket open and you're going to receive events, right? Part of the philosophy in this is that everything is very, if you think of traditional databases as a single source of truth, that's a very objective worldview, and we're moving very much into a subjective one, where different people will interpret different data and have care about different parts of the data as well. So this is also ends up in a bit of when we talk about how we serialize the data, right? Is it kept on disk as a stream? Probably not, because we need to have random access into the data, right? And we could keep a stream as a index, but we don't have to, right? And even for things like doing remote selection, this is a completely unsolved problem for us right now. On public data or on data that remote node can see, yeah, you can send them a query and say, give me the things that match this. But when it's storing encrypted at rest data that it doesn't have the keys to, there isn't really a good solution here other than pulling the whole thing down or pulling little bits at a time, analyzing it and saying, the next bit I need would be labeled like this. Can you send me this next piece, right? So there's some work to be done there. And
one second. That's exactly the beauty. If you can send the query, it can work on using their keys, and then they would validate that the query structure doesn't expose them. Like they can accept this query is fine, so I can run it on my private data.
Right, but they don't have the keys. They're just a store and forward mechanism.
No, I was thinking the peers, the ones who have the keys.
So the peers may be offline is the problem.
Yes, that's
right.
Life.
Yeah.
But then if they're offline, that means you're not getting activity because they're not. The whole point of a stream is when they come offline or when they're active, you get to catch up.
If it's structured as a stream, yeah, absolutely.
So one of the things Brooke is talking about here is the possibility of having agents that basically expose like a private information retrieval system where they can act as almost like a mailbox or like a PO box for your data, and encrypted data that's meant for you that they do not have access to can be stored in their store, which you can then pull down even if the originator of that data is offline.
So for example, and this is actually not the mailbox case, but there are two peers that are communicating. It's Philip and Quinn. And Philip makes a bunch of changes to his store and synchronizes those to Fission's data service. Doesn't want Fission to see the data. Closes his laptop, he's offline. Quinn wants to make queries against his data store, right? So now the options are, at least to get started, are relatively limited, right? You can pull the entire thing, decrypt it because she has keys, go through the data, or can do a little bit at a time, pulling back and forth. There are encryption mechanisms that expose, or that with a key, you can find, hey, all of these match my secrets, therefore they all have this attribute, for example, right? So there are options in there, but this is just something that we haven't really explored. We haven't explored yet.
I may be wrong, but what I'm thinking is that when you have the graph of activities, you can have each step of the graph on different encryption key. So
yes,
I can say I'm publishing, but I'm also publishing the intermediate results, and this one I'm giving access to Quinn for this one, which happens to be a slice, and I know the slice he's interested in, as opposed to what I'm showing to other people. So the idea is to create these, not just my main encrypted stuff, but the slices of computations, if that's been sent to me, and those can have different capabilities attached to them with a different key. And then it.
Yeah, so if the provider of the data knows about your specific use case and is going to collaborate on it, absolutely, there's more optimization.
And this is why sending the query makes sense. Like, I've received this query from Quinn, so I know, okay, I've accepted this Quinn proxy agent as part of my data flow. And that becomes another stream that Quinn can read.
Almost like Lambda, but for data log.
Yeah, well, it's about, the idea is if you're making these streams of intermediate results, they have value intrinsically, and subscribing to them can make sense.
We actually are over time right now. Does anybody have any final burning questions before we wrap up? Great.
Very impressive.
Thanks everyone for coming along. Thank you, Quinn, for the fabulous presentation. And we'll see you all next month.
Thanks for joining, everyone.
Goodbye.